All right, so today we're going to have a look at proving de Moivre's theorem. So there's 3 steps to it. The first one should be pretty familiar, and then we'll follow through all 3 to prove it for all rational numbers. Okay, so this is it. This is de Moivre's theorem. We've already seen it, and it's above, and it is proof for all of z that belongs to this Q. And like I said just before, this Q represents rational numbers. And what rational numbers are is, it's all of the integers. So, from negative infinity all the way to positive infinity, but only the rational numbers, so 1, 2, -7, those numbers. But it also includes any fraction with one of these numbers on the top or bottom, so like 3/2 or -3/2. So that's what this rational number means. We're going to prove it for all. All right, so the first thing we're going to do is we're going to prove it for positive integers. And we might remember doing this just before, and it might look familiar because we did it when we looked at our induction. So the first thing we did with induction was we wrote P of n. P of n is, and then we're just going to rewrite out de Moivre's theorem. So the modulus of cis theta, all to the power of n, equals the modulus to the power of n, cis of n theta. Okay, so the next thing we did was for number 1, we wrote for P of 1, oops, not P of I, P of 1, we get the modulus of cis theta to the power of 1 equals the modulus to the power of 1 cis of 1 times theta. All right, we can simplify both of these sides to be modulus of z cis theta equals the modulus of z cis theta. So therefore, P of 1 is true. Okay, so that's always, like always, step 1. All right, so now we're going to go to step number 2. And we always start by defining our P of k. So we're going to say if P of k is true, then modulus of z cis theta to the power of k equals modulus of z to the power of k cis k theta. And this is going to be really useful in a moment when we have a look at P of k plus 1. So now for P of k plus 1, now for P of k plus 1, z cis theta to the power of k plus 1 equals modulus of z to the power of k plus 1 cis of k plus 1 theta. All right, so far it just looks exactly like induction, and it's going to keep doing so for these positive integers. All right, so let's expand this out. So when we have k plus 1, it means we're doing the power of k, so the modulus of z cis theta, the power of k, multiplied by the same thing, modulus of z cis theta to the power of 1. So those things are equivalent. Now, what we've done is we've isolated this term here. Let me highlight in a different color. We've isolated this term here, which we knew from above. The reason we wrote this out is we could rewrite it like this. So that's what we're going to do. All right, so let's substitute that in. So the modulus of z to the power of k cis k theta times by, So that whole thing multiplied by, we can drop the 1 because we know the power of 1 is just this original thing, cis theta. All right, so what we've done now is we've written it in a form, and we can hopefully simplify it from here and get it to the right-hand side. Okay, so what we get here is we can see we've got this modulus of z times by modulus of z. And we know that when we have just a number, it's always to the power of 1. So when we're multiplying, it doesn't matter which order we do it in. So we're going to gather those together. So that would be the modulus of z to the power of k times by modulus of z to the power of 1. All right, so we gather those. Now, what we're left with as well is this multiplied by cis of k theta. And the other thing we're left with is this cis of theta by itself. So another multiply cis of theta. All right. Now, when we have two numbers multiplied by each other and they've got the same base, it means we can add the powers. So that's what we'll do. We'll just add these powers, and what we're left with is something familiar looking. So the modulus of z to the power of, we started with k, we've got an extra 1, k plus 1. And when we multiply cis, when we multiply them, it's the same as adding them. Okay, and when we divide them, it's the same as subtracting the inner part. So we can rewrite this as cis of k theta plus theta. All right. So another way of writing that, the first part, it looks pretty similar. So we've got this original part here. And we can make it the second part because we know we can rewrite. So that first modulus of z to the power of k plus 1, that's good, looking good for us. But the second part, we know we can see there's a theta in both of these components. So if we remove that, so cis of k plus 1 all times by theta, we can see if we multiply that theta in, we get the same thing. So what we've got is we've proven that this works for k plus 1. So we're not doing induction now, so I'm not going to write it out, but this is where we write. So it works for p of, so it's true for p of 1, and when p of k is true, it works for p of 1, so therefore we've proven p of n. All right, so we have proven this part here for real positive integers. Okay, now we just have to expand it to include all of the integers. All right, so the next thing we can do is we can prove it for all integers z. All right, and the first thing we can do is we can observe that this is going to seem pretty random, but you'll see why we do it in a minute. Cis of negative n theta. All right, so what we're going to do, we're going to expand this negative, well, add a negative in there, and that's the same thing as cis of 0 minus n theta. Okay, so we haven't done anything, so 0 minus is just going to be the minus. But what we can do is we can rewrite this as cis of 0 divided by cis of negative n theta. All right, and the reason for that is if we just write our little rule here, cis of phi divided by cis of theta is the same thing as cis of phi minus theta. All right, so using that rule, we've rearranged this. All right, now we can break it down, but cis of 0 is equal to the 1 divided by cis of negative n theta. All right, now the reason cis of 0 is 1 is because we get cosine of 0. If you put that in your calculator or you look on your unit circle, that equals 1 plus I sine 0 if you put sine of 0 in your calculator or look on unit circle, that's 0. So you're going to get 1 plus 0, which is equal to 1. So that's the reason for this. So next thing we're going to do is, oops, sorry, when I put this underneath, I should have left it as change it to a positive, because the negative means turn it into a fraction. So that should be a positive value there. All right. So the next thing I can do is write this as 1 over cis theta to the power of n. Okay, so that's another rule. When we have the power of cis, we can just bring it down in front. All right, so that's going to be true, and we can then rewrite this. If we put this back to the top, we can say this is equal to cis of theta to the power of negative n. Okay, so what we get is, because we've got this negative here, we can say, so the theorem is true for all, that's for all, n belonging to our integers. Okay, and that can be plus or minus. So the last thing we want to do is, so we've proved it for our positive integers, we've proved it for our regular integers, and the last thing we want to do is prove it for our original statement. All right, so for our rational numbers. All right, so finally we'll prove it for all of our rational functions. So we're going to consider that n is the same as p over q. All right, so it's going to be a fraction where p and q belong to the integers. Okay, so they're just numbers, so it can be, I don't know, 3 over 2 or whatever. It can be negative as well. So that's what we're going to start with. We'll also have a look at a couple of things. So this is just to set ourselves up. So we're going to say cis of theta over q to the power of q is the same thing as cis of q theta over q. Okay, we've used all these rules before, and we can see that if we did this, that would cancel that, and this would just be the same thing as cis of theta. All right, the reason we can do that is the same rule we used down here when we had the powers. Okay, so that last little rule we used. The next thing is, we can do the same. Well, if we know this, we can therefore say that cis of theta to the power of 1 over q is equal to cis of theta over q. All right, seems pretty weird, but that's how we're setting it up because of the next part now. So therefore, cis of theta to the power of p over q, which looks a little bit more like what we want to prove, is the same thing as cis of theta to the power of 1 on q all to the power of p. All right, so that's how exponentials work. We can just keep expanding them, which equals cis of theta over q to the power of p, which equals cis of p over q theta. All right, so therefore, the theorem is true for all rational numbers q. All right, that's my fancy q. I'm very bad at drawing those. So you can be asked to do this. This is part of the course. You can be asked to derive de Moivre's theorem or prove de Moivre's theorem. So yeah, that's how you do it for all q. Thank you.